Welcome to EF5 training, Module 2.2 from the University of Oklahoma Hydrometeorology and Remote Sensing Group. My name is Laura Lavriola. Today, for this presentation, we'll be doing inundation modeling. The outline for this will be learning about inundation, looking at rating curves, looking at inundation in EF5, readying the control file, we'll do an example, and then we'll look at how to understand these results. Inundation is an important aspect to be cautious of because when floods of any kinds occurs. Before we can start modeling inundation though, let's learn about what goes into it. The inundation method used in this example is the simple inundation approach. So we're going to look at this simple inundation approach. This approach was outlined in Bates and Rue 2000, which uses a kinematic wave approximation for high-resolution topographical files. And this paper is also included in your EF5 advanced folders in the documents. So this idea is, if the height of the water is greater than the height of the DEM, the water will end up overflowing into its neighboring cells. So this is how inundation is created in this approach. In EF5, in order to do inundation modeling in EF5, you'll need to know the rating curve. So there are two equations that are commonly fitted to stage discharge data, but we will focus on the following, which is used in EF5. It's where stream flow is equal to alpha multiplied by the stage height raised to the beta. So what you'll need to know is your alpha and beta measurements, because then when we simulate stream flow, we can also calculate the height. So if you know the fitting of the stage discharge data, you can use that alpha and beta in EF5. Once you have A and B, you can begin to set up your model to run for inundation. Next, we will go over how to set up your control file after we briefly talk about high-resolution topographical files and inundation. So this was an example from a flooding event in Colombia. We used high-resolution DEMs like the SRTM2 dataset, which lets us go beyond stream flow into the realm of inundation modeling. So to the right is an inundation along the Bogota River in April 2002. So we can see how the flood spread and the depth of it. With this high-resolution data, we can use really fine data to actually simulate how far the inundation extent goes. So we can further look at this in this example. So this is just a still from one of the inundations from the last slide. But what this means is that we can further zoom in to different parts of that river and still get really accurate and fine, detailed resolution. So using this high-resolution data has pros and cons. The advantages of it is that we can use high-resolution inundation modeling, and that is a little bit more useful than using just pure stream flow for most users. We want to know where the flooding is going to go, and sometimes stream flow doesn't really give us that kind of information. It can also lead to more accurate simulations because we have better data values. Using high resolution is also physically realistic, and that can also open the door to simulations on small basins, which usually don't have very good data values. We can also use high-resolution data to forecast for flash flooding. However, this comes with a few disadvantages. The cons are that these file sizes are really big, and so that means it's going to be longer run times for you to simulate and calibrate on, and it's also very complex because you have so much data to work with. So we've created a little bit of comparison to walk you through different types of resolutions. So we created an SRTM2, DEM, FAC, and FDR for the Bogota River example that we looked at a few slides ago. Each file size is 7,200 by 7,200 pixels. And then for comparison, a 2-kilometer grid with that many pixels would cover almost the entire surface of the Earth. Each 2-kilometer grid we created and ran for the Bogota example is 40 kilobytes. So the SRTM2 data is about 2,000 times larger. So this is really fine data that we used our inundation example for. So now we're going to actually look at Bogota River grids at a bunch of different resolutions over the domain. So the first example is a 4-kilometer DEM. So this grid is 50 by 50 cells, and it's only about 5 kilobytes big. And as you can see, the resolution's pretty coarse. You can see the squares, and you can't really tell where the rivers are. However, as we get into 2-kilometer DEMs, where it's 100 by 100 grid cells, so that's double the resolution of the previous one, it's a little bit higher size of 40 kilobytes. We can actually start to see rivers, and you don't see the squares as much. So now as we get into finer resolution, we're getting to 30 arc seconds or 1-kilometer DEM. This is 240 by 240 grid cells, and this is about 100 kilobytes, so double of the last one. We can really start seeing the finer resolution of the rivers and the features of the land. The next one is 30 meters, which is 1 arc second. And so this is 7,200 by 7,200 cells, so this is a lot. These are really fine cells, and you can really see that. However, this is 100 megabytes. So I'm going to go back and forth between the 1-kilometer and the 30-meter data. So looking at it from this far away for our domain size, you can't really see too much of a difference. You can still see the same rivers. It's just a little bit more pronounced in the 30-meter. So for this domain size, you could probably get away with doing a 1-kilometer DEM because we can still pretty much see all of the important details. So as I said, at our basin scale, it's easy to see the difference between the 4-kilometer, the 2-kilometer, and the 1-kilometer grids. However, when we compare just the 1-kilometer and the 30-meter grids, it looked pretty similar. However, if we just zoom in one more time, we can really illustrate this point. So when we zoomed in pretty far in, this is the 1-kilometer or 30 arc second DEM. And this is 90 by 90 grid cells, and it's about 35 kilobytes. And it's pretty coarse resolution. However, if we switch to the 30-meter or the 1 arc second DEM, it's 2,700 by 2,700 cells. It's about 14 megabytes. But you can really see the difference between the coarse and the high resolution. You can make out the rivers much more. You can see the variability of the land. We're also going to show you the flow accumulation of the 2-kilometer, which is 30 by 35 cells, which is only about 5 kilobytes, compared to the 30-meter or 1 arc second FAC. So if you're looking at this on the presentation of the video, you might not see it as well. But if you go into the PowerPoint and you zoom in really well, you can actually see how fine these rivers are compared to the big blocky ones of the 2 kilometers. So as you can see, the SRTM2 data has major advantages for the following uses. We can accurately model over small basins, which are less than 1,000 square kilometers, or we can use this for flash flooding applications. The advantage of using high resolution models is also because we can use this for inundation modeling. So however, to get the most out of your SRTM2 data set, you have to make sure you have plenty of memory processing power, and disk space. And something very important to know is that you should calibrate on a coarser resolution grid, and then you can run the simulation on the high resolution SRTM2 grid to save time. Okay, so now that we've gone over resolutions and how we can use them, we're ready to use our control file. So there's a few things that we need to edit on the control file. So to use inundation modeling, we need to add a parameter set. So I've added it in between crust param set and KW param set. And the new block is going to be called simple inundation param set. And this one was named Nazoya, and it's highlighted in the first red rectangle. Then you're going to add the gauge that you're going to be putting the parameters on, as well as the alpha and beta values that you've gotten from your discharge data. The next three important lines to put is in your task file or in your task block. These are inundation is equal to simple inundation, so you're saying which modeling inundation we're going to be using, and that's simple inundation. You're then going to put the inundation underscore param underscore set. And that calls to that simple inundation param set that we put in between the crest param set and the KW param set. Finally, the last line that you're going to use is called output grids. And what this does is it's going to output these inundations into a grid so you can visualize it in QGIS or whatever program that you can upload TIFFs in. So go ahead and fill these lines in your control text file. You can find this control text in your examples folder, Nazoya, and then in your inundation underscore example. You can go ahead and pause that and then resume when you have filled in your control text file. Once you do that, go ahead and save it. You'll navigate into your inundation example folder. You'll locate your EF5.batch file, and you'll go ahead and double click it. Next, you'll wait for EF5 to finish. So now let's zoom into my computer so then we can follow along together. So looking at my computer screen, we can see that the simulation is over because it has done as the last line. So we can go ahead and exit out of the two pop-ups, and then we'll navigate to our inundation example output. And so you should have some images that look pretty similar to mine, as well as a time series output through Excel. So next what we're going to do is we're going to go on QGIS and we're going to explore how we can visualize this inundation. So we'll go ahead and go into QGIS. We'll go to raster, or we're going to go to layer, add raster layer. We're going to navigate to Nazoya, and this was our inundation example. So we're going to double click this folder. We'll navigate to output, and we'll click on just any one of these that you want to. So we'll go ahead and press open. And what we're going to do is we're going to change these colors around a little bit. So we're able to do that if we go to our layers and we right click and we say properties, and we're going to click properties. From here, we're going to go to render type, and we're going to change that to single band pseudo color. And so we want to kind of, maybe inundation would be nice if it was a blue color. So we're going to change it to a color map of blues. And so that's this first option I see. We're going to then press classify, and then that will divide all the numbers up to the inundation values. So we can go ahead and press apply and see how that looks on our map. We can even see the Nazoya River Basin output outline that surrounds the inundation area. Next, what we can do is we can actually change the color of this 0 value. So what you're going to do is you're going to double click on this square that's underneath the color option. So I'm going to double click right here, and this shows up. So what you can either do is you can change the opacity of it. So if you have a base map already loaded into QGIS, if you put the opacity is equal to 0, then all that's left will be the actual river and inundation blue colors that are shown. However, I don't have a base map on here right now, so I'm actually going to make the color a grayish color. And I'll put the opacity all the way up. So I'm going to press OK, and then apply. So now I can, and I'll press OK one more time. So now I can visualize the Nizoya River Basin and what the inundation around it looks like. As an important note, these values are not verified and they should not be used for forecasts or warnings. You should always make sure that the values are calibrated and that you compare them to observations to see how well the inundation model actually did. The purpose of this module is only to teach how to produce inundation maps. Thank you very much for joining us for the inundation module 2.2. Please join us for the next module, which is multiple gauges and output grids. Thank you very much.